I'm happy to announce our speaker today, Dr. Dani Szpruch from Open University, and he will speak about the metrics of local coefficients and the restriction problem. Please go ahead, Dani.
Yes, I think I say very little about the restriction problem. Thank you very much, Professor Kuniavsky, for inviting me. It's a great honor. So I will tell you today about my project with Fan Gao and Freedun Shahidi on the metrics of local coefficients. And let me start with some fundamental definitions and results regarding representation theory, just to have everybody on board. So let G be a group. A representation sigma of G is a homomorphism from G to the linear transformation, invertible linear transformation of a complex vector space V. A representation is called irreducible if it has no non-trivial invariant subspaces under this action of G. If G is abelian, for example, then all its irreducible representations are one-dimensional, namely homomorphisms to C star. The collection of all unitary characters of a group is called the dual group of G, and it's denoted by G hat. If we have two representations of a group, then a linear map from one underlying vector space to the other is called an intertwining map if it's commute with these two actions of G. And the space of all intertwining maps is a vector space denoted by home G sigma comma pi. If T is invertible, then we actually say that pi and sigma are the same, namely they're isomorphic, they lie in the same isomorphism class. If sigma and pi happens to be the same representation, then we are talking about a self-intertwining operator. And this collection of self-intertwining operators is actually an algebra, which is called the commuting algebra of sigma. Let's assume for a moment that sigma is unitary. This is an important example. A representation is unitary if it preserves an inner product. So sigma is actually a direct sum of irreducible representations. And sigma is irreducible if and only if its commuting algebra is one-dimensional. And more generally, the dimension of the commuting algebra tell us how reducible sigma is. For example, if the dimension is 2, then sigma is a direct sum of two irreducible representations, and vice versa. It is not true, however, that if the dimension would have been 4, it means that sigma is a sum of 4 irreducible representations. Any representation of a finite group is unitary. This is why the theory of a representation of finite group is so nice. Here are the basic problems in representation theory. First, classify all the irreducible representation of a group G. And second, find all irreducible G invariant subspaces of a representation arising naturally in some context. Let it be number theoretic context like I would discuss today, or combinatorics, or graph theory, probability. I mean, representation theory is everywhere. And let me discuss standard construction in representation theory. You start with a subgroup B of G. Hopefully, you understand the representation theory of B much better than the representation theory of G. You pick a representation of B, and then you consider all the space of functions from G to the representation space, which has the following equivariant property. When you translate G from the left by an element of your subgroup B, then tau B acts on Fg. For example, if B is the trivial group and you pick the trivial representation, the one-dimensional trivial representation, then what you have here is the space of all functions on G, L2G. So induction is generalization of this important space.
But here you assume something when you write L2, then G is topological or finite or?
I'm being really ambiguous here. I'm not just what I really wanted to say that if you are looking at induction from the trivial representation of the trivial group, then you are looking at all functions. And of course, once you discuss infinite group, you usually discuss topological group, and then there are tons of continuity and smoothness requirements. You're absolutely right. And then this induced space is a representation space. G acts on these functions by translations from the right. This construction has many nice properties. I think the most important is Frobenius reciprocity. It's telling you that to analyze the commuting algebra of a given representation sigma and this induced representation, it is like analyzing this space, and this H should have been B. It's like analyzing the homomorphism as B representation of the restriction of sigma and the inducing representation. And this is a typo. B should have been H. H should have been V. Clifford theory that some of you may heard of tells you when an induction is reducible. Generally, if you have a representation of this subgroup B and you pick an element of G which normalizes B, then you can define a new representation. Typically, of course, not isomorphic to the one you started with. C twisted by the sigma twisted by G. If B happens to be a normal subgroup of G, then the induced representation is irreducible if and only if sigma is irreducible. Otherwise, there is no chance. And there is no symmetry here. None of the twists of sigma by elements of G which lie outside B are isomorphic to sigma. I would like now to discuss the example of induced representation on SL2 over finite fields. The main goal of my talk is to reproduce some of the results from the finite field case for p-adic groups and then for coverings, for p-adic SL2 and then for coverings, eventually for coverings of p-adic SL2. So we pick a finite field and we are looking at SL2K, which is the group of 2 by 2 matrices over G with determinant equal 1. We have there the subgroup of upper triangular unipotent matrices, namely these matrices. And we have here the diagonal subgroup. Of course, the unipotents are isomorphic to the ground field. I mean, once you multiply these two matrices, the coordinates would add up here. And as we all know, the diagonal subgroup is isomorphic to the invertible, to the multiplicative group of invertibles and elements in K. Then the group of upper triangular matrices B is a semi-direct product of U and H. Then we have this guy, which is typically called as a Weil element. It normalizes the torus, the diagonal subgroup. Moreover, this is the only non-trivial normalizer of the torus modulo the torus, of course. And these two subgroups and the Weil element generate SL2. Any representation of H may be extended trivially on the unipotent subgroup to a representation of BK. And we shall not distinguish today between representation of H and representation of B. Now, a representation pi of SL2 is called supercuspidal if it does not contain any non-zero UK fixed vector. The word supercuspidals come from historically from modular form. Supercuspidal modular form is a modular form whose constant Fourier coefficient vanish. And this can be shown to be an exact analog for that definition. And it turns out that all irreducible representations of SL2K are either isomorphic, are either supercuspidal or some irreducible subrepresentation of this induced representation, inducing from an irreducible representation of the torus extended to the upper triangular matrices 2SL2. This is a consequence of Frobenius reciprocity. And of
So
course, come again?
So these are the principal series.
Yes.
Or the quotients are the principal series.
Yeah, I mean, the direct summands inside principal series representation, as long as we stick with the finite field. And the representation of HK of the torus are just character. This is an abelian group. And as Eyal said, IK is called the principal series representation. And here are the natural problems. Find the criteria for irreducibility of this IK. Describe the commuting algebra. Describe the redundancy. Precisely, I mean, what do two different induced representations of this type has in common? Mackey theory, which is not too far from Clifford theory, tells us the story here. IK is irreducible if and only if conjugating chi by W, as explained earlier, is not isomorphic to chi. Since chi is one-dimensional, then isomorphic being actually equal. Since chi, you can compute it. Chi twisted by W is just chi inverse because W just swaps the two coordinates of the torus. It follows that IK is reducible if and only if it's a quadratic character. Yes, IK is reducible if and only if chi is a quadratic character. When it is reducible, and it's a sum of two irreducible representations. And those two different inductions have nothing in common unless chi prime is either chi or chi inverse. In this case, they're actually isomorphic. And I want to describe explicitly an intertwining map between these two inductions. You can construct a linear map from IK to IK inverse using this summation. I mean, to check that this is actually an intertwining map, we should check first that there is this is once we hit G from the left by a unipotent element, this sum is unchanged, which is completely clear by virtue of changing variable. Then we have to see that the action of T is conjugated by the Veil element. This is the Veil element, and this is precisely what we have here. This is precisely why it stands here. Anyway, this is well-defined, the non-zero element in this space of homomorphism. This is the one we are looking for. And moreover, when chi and chi inverse are the same, this is not a scalar map. And recall that in this case, when chi equal chi inverse, the commuting algebra should be two-dimensional. So here is the non-constant generator. I now want to move to p-adic fields. And before I tell you the p-adic analog of this story, I have to introduce some arithmetic factors. So first, the standard definition of p-adic fields. We have the ring of integers, and we have the unique maximal ideal. The quotient OF modulo PF is a finite field whose cardinality is denoted by Q. We have a generator of the maximal ideal, and we normalize the absolute value of on F so that the absolute value of the generator, A generator, is Q to the -1.
But F is still finite, right?
No.
No. Okay. Characteristic 0.
Yeah, I should have said. I mean, this is missing here. Let F be a finite field. Yeah. So I mean, F wasn't introduced before, and I'm missing here a line. F is p-adic field. This is the second type for today. If dx is a Haar measure on F, then d star x, which is dx over the absolute value of x, is a Haar measure on F star. We have a Fourier transform. We fix an untrivial character of F, psi. Then all the other characters of F have this form. It is of the form psi ax, which is psi of x multiplied by a. This is an isomorphism from F to its dual subgroup, to its dual group. Let SF be the space of Schwartz functions on F. And we have the psi Fourier transform, right? I mean, the standard one. Take your Schwartz function and integrate it against the psi as a kernel. D psi is the self-dual Haar measure on it, so that when you apply Fourier transform twice, and then you hit almost on the same function you started with. And here are equivariant functionals. This is the local portion of the state thesis. F star is acting on SF by right translations. And if we have a character of F star, then we define a psi to be a chi equivariant functional if it translates nicely. I mean, when you translate your function by X and act by the functional, then you have chi inverse coming out. And there should have been here a sub-index. Define SF chi to be the space of chi invariant, chi equivariant functional on SF. And a theorem implicit already in Tate thesis and made explicit by Weil, the dimension of this space is 1. Up to a scalar, there is only one functional, non-zero functional with this property. And how do we construct one? Well, I mean, if it were a finite field, then we can just take the sum phi times chi, and this would have worked. But we are no longer in a finite field. So we introduce a complex parameter S, and we integrate this way. The outcome converges to a rational function in Q to the minus S in some right half plane. And obviously, if this integral converges, then this is by changing of integration variable, this is a function we wanted. And its meromorphic function is called the zeta integral, or sometimes the Mellin transform. It turned out that all these zeta integrals has the inverse of an L function, local L function, as a common denominator. Let me remind you that the local L function is trivial if chi is ramified, and otherwise we have this quotient. Chi is said to be unramified if it's trivial on the in-periodic units. This means that if you cancel the poles of the zeta integral, you end up with a non-zero element in SF hat chi. Chi S being, of course, chi twisted by absolute value S. So we found a non-zero element in this one-dimensional space. Now it is an exercise to show that if you replace chi by chi inverse and S by 1 minus S, you get another element in the same, non-zero element in the same one-dimensional space. Which means that they are proportional. There is a proportional function denoted by epsilon. It must be non-zero. It must be a monomial in Q to the minus S. So, I mean, if it's a rational function in Q to the minus S and monomial, then it must be, and non-zero, it must be a monomial in Q to the minus S. And in fact, it's a monomial times some, I mean, the coefficient is just a Gauss sum. And Tate gamma factor is defined just by moving this term to the other side. So it satisfies a functional equation relating the two zeta integrals. Once you plug a nice enough test function, this function supported near 1, you get the gamma factor as a value of a certain integral. It converges in some, this principal value integral converges in some right half space, and in fact the sequence can stabilize. Next, for the sake of covering groups to come, I have to define the nth power Hilbert symbol. We fix an integer n, and we assume that f contains all the nth root of 1. We denote this cyclic group by mu n, And we identify it once and for all with the nth root of 1 and C star and forget about this identification. We have the nth power Hilbert symbol. This is a map from F star times F star to mu n. The nth power Hilbert symbol is an anti-symmetric bilinear form on F star. In the special case where n is 2, then this is also a symmetric bilinear form, just because the inverse of -1 is -1, right? If n equal 2, then it goes to ±1. This is an undegenerate form. Precisely, if you pick an element in F star, and you form the character eta A of C, of eta A, by sending C to the Hilbert symbol of A and C, then you identify by this means F star modulo the nth power with its dual group. Those are finite groups. We have another cousin of Tate gamma factor, called Weyl index. There exists a map from F star to mu4 with the following remarkable property. I mean, gamma psi of AB is gamma psi of A times gamma psi of B times the Hilbert symbol. In other words, this map A goes to a gamma psi A splits the quadratic Hilbert symbol. This map is called the normalized Weyl index. And why did I claim it's a cousin of Tate gamma factor? Because if A is an element of F star and eta A is a quadratic character associated by A, as explained above, by the quadratic Hilbert symbol, by the n equal 2 case, then it turns out that gamma psi A is nothing but an epsilon factor. This was proven in the 80s by Bruno Kahn and then utilized here and there, say, by Ichino. I happened to hit on this assertion a few years ago using the same techniques I'm using for what I'll tell you in a few minutes. So I have an independent and shorter harmonic analytic proof of this identity. Last, I need to introduce another arithmetic factor, which plays an analogous role to Tate gamma factor when you do covering groups or some covering groups. You can modify the definition of Fourier transform by changing the kernel. I mean, we are throwing in this Weyl index. What you get is not a Schwartz function. It's not even a function defined at 0. But the point is that the zeta integral of this transformed function converges absolutely in some vertical strip. Moreover, this gives you a natural definition of zeta of this transformed function. And we have a functional equation very similar to Tate's functional equation, only we've changed the kernel. So we get a different gamma factor. This is what I call the metaplectic gamma factor. And if you plug a nice test function, then you can express this as an integral. This is the same integral as the Tate integral, only we have the Weyl index inside. So I defined the gamma factor some 15 years ago, but in fact, this integral already appeared in the work of J. Sweet in the mid-90s. So while the gamma factor, the metaplectic gamma factor is new relatively. I mean, it's first appeared in my work on the double cover of SP2 to N, and as I will show you, it surfaces again in our current project. The integral, though, appears quite frequently. I mean, when you study double covers or some evenfold covers. So J. Sweet first ran into it in the mid-90s. And then Eyal Kaplan, sitting here, ran into it, I think, in 2 different projects. So one with Adrian and the other with Fram. And Nelson also had a paper with it just very recently. So the value of this integral actually matters. And it turned out that it is more or less a quotient of 2 gamma factors. This is just chi inverse, chi of -1, not very interesting. And this is just an innocent eighth root of 1. And I don't want to get into details of what exactly this factor is. This integral was first computed by Sweet, although he never published it. I mean, it was a preprint, it wasn't even available online, and then somewhere in the late 90s, he quitted mathematics. I never knew about this preprint, and then I brute force, I computed it brute force some 15 years ago, or almost brute force. I mean, I had just to extract the analytic properties of this. Then I learned about the proof of Sweet and published it in some appendix. Just very recently, I had a simple proof of this identity, which actually is important. The analytic properties of this factor are important. Eyal can tell you about this. So now going back to SL2 over p-adic fields, I want to tell you how far we can push the finite field theory and where do we start seeing analytic functions, some meromorphic functions. We studied those principal series for the same motivations. We actually have more motivations because these ones are local components almost everywhere of endomorphic form. Bruhat theory tells you that the I-chi is either irreducible or has a Jordan-Helder of length 2. This is the analog of the I-chi in the finite field being either irreducible or a sum of two irreducibles. I-chi and I-chi inverse, although not isomorphic, have the same Jordan-Helder series. And if chi prime is not chi or chi inverse, then they have nothing in common. If chi is not quadratic, then the commuting algebra is one-dimensional. This means that if chi is not a quadratic character, then chi is irreducible. So far we are actually having like the same results as in the finite field theory. And here is where the two theories diverge. It is the fact that I1 is irreducible. I mean, the most symmetric quadratic character give you an irreducible representation. This is a difference between p-adic theory and finite field theory. And I'll now introduce the intertwining operator and then explain how to deal with the I1. I mean, how to explain the fact that it is an irreducible, contrary to the finite field theory. First, intertwining operator. So we would like to define an analog to this finite sum we had before. So an analog of finite sum should be an integral. The point is that integrals do not always converge. So what we do, we introduce a complex parameter S and take meromorphic extension. So we consider this family of induced representation. Of course, when you vary S, then your representation are not isomorphics. And then you introduce a section of functions depending analytically on S, each belong to the induced space. And then we can consider the exact analog to the finite sum that we had. This sum converges in some right half plane to a rational function in Q to the minus S, and then we take its meromorphic continuation, which is exactly the intertwining operator. And here is where the analytic structure pays off. Plancherel measure and Knapp-Stein dimension theorems. So as explained earlier, for an open Zariski set inside C, these intertwining operators are analytic and the commuting algebra is one-dimensional. This means that if we take the intertwining operator in one direction and then we compose it back with the intertwining direction from the other direction, then we hit on a scalar map. This scalar must be a rational function in Q to the minus S. And it is called the Plancherel measure associated with chi. And Knapp-Stein tells you that your commuting algebra would be two-dimensional if and only if chi is a square and the Plancherel measure or the inverse of the Plancherel measure is analytic at S equals 0. This means, for example, that and in this case, this is a non-scalar operator. And this means that when you take a quadratic character, then I chi is reducible if and only if the Plancherel measure is analytic at S equals 0. So this completely shifts the question of reducibility of this induced representation to the study of this meromorphic function. Now it's a good question how to compute it. I mean, there is no natural test function we can plug here, at least not for higher rank groups. So it will give us, I mean, there is no nice test function that will give you this scalar. We have to tackle it in another way. Let me introduce it now. We say that sigma is okay, so we start with the representation of SL2. I mean, I did not introduce the word smooth before, but there is some smoothness requirement here. A functional psi sigma is called a Whittaker functional if, when you act on your vector by a unipotent element, then you have a psi coming out. Recall that the unipotent subgroup is isomorphic to the field, to the ground field. And we denote the W sigma psi, the space of psi Whittaker functionals. The space of Whittaker functional is nothing but the space of homomorphism from U of sigma. Maybe I should have written here sigma restricted to U to the space, the one-dimensional spaces on which the psi acts. And let me construct explicit Whittaker functional on the space of induced representations. This integral, if it converges, is clearly a psi equivariant functional, again just by means of changing integration variable. And this W here assures us that the integral would converge in some right half plane. This is why it's here. This is called often in the literature Jacquet type integral. It has an analytic continuation to the whole complex plane. And this gives us Fs goes to this functional applied on it is a non-zero psi Whittaker functional. Note that whenever we have, now for any two representation of SL2F, whenever we have an intertwining map, we have an intertwining map between the Whittaker spaces in the opposite direction, as usual, by composing psi with the operator. I mean, it's always the same story. If you have a linear map from one vector space to another, then you have a map on the space of functionals from the other way around. In the case where this is a self-intertwining map and a self-intertwining scalar map, then A psi and A, and if A is scalar, then A psi is also a scalar. This means, for example, that in the context of irreducible representation, of principal series representations, if we would compose these two Whittaker maps, then we would hit on the Plancherel measure. So now we are shifting the burden of computing this scalar as a scalar coming from composing two maps on this huge space of induced representation to the hopefully better understood space of Whittaker functionals. And how good is the situation? I mean, as good as it gets. The space of irreducible representation is infinite dimensional, and the space of Whittaker functionals is one dimensional. This is a theorem proven by different mathematicians in increasing order of generality, Shalaika, Gelfand-Kazhdan, Berendt and Levinsky. If sigma is either smooth irreducible representation of SL2F or induced representation from this Borel subgroup, then the space of Whittaker functionals is at most one dimensional. And this theorem holds for any quasi-split algebraic group and its parabolic induction of it. This is a theorem that holds in great generality. So uniqueness of Whittaker model give rise to Shahidi local coefficients. Since these two elements are two functionals in the same one-dimensional space, then there must be a proportion function. This function is called Shahidi local coefficient, or to be exact, This is the reciprocal of Shahidi local coefficient. These two functionals, these two Jacquet integrals I introduced before, arise really naturally when you take Euler product of certain Fourier coefficients of Eisenstein series. And these coefficients are Eulerian due to the uniqueness of Whittaker model. I do want to note that, I mean, this observation is not so important for algebraic group, but very important for what to come. That these two gammas actually identify the two underlying Whittaker spaces with one vector space, the space of functionals on the inducing character. So this means that we can view this scalar as a 1-by-1 matrix representing a map between one vector to itself, one vector space to itself. I mean, we have identified these two Whittaker spaces. If you take a nice space function, this you can actually do, then you can compute, you can reduce this local coefficient to a value of a local integral. This is the same integral we've seen before. Shahidi local coefficient in this case is Tate gamma factor. And this is why people care so much about these coefficients, because they appear as local components of RTL functions. And more generally, when you play this game with other parabolic induction, this is the actual way to define gamma factors and global L functions eventually. Since we already know that the product of these coefficients is a Plancherel measure, we actually computed it. We have explicit formulas for Tate factor, Tate gamma factor. And from here, you can actually extract the reducibility result. I chi is reducible if only if chi is a non-trivial quadratic character. I mean, when chi equal 1, then you'll actually have a pole coming from here. So this is more or less the end of the story as for p-adic algebraic groups. And I would like to move to the main object of study, which is the metaplectic groups. So the covering of by metaplectic group for this talk, I mean n-fold cover of SL2 by mu n. This is a certain topological extension, non-split one. So we have mu n sitting in the center of this n-fold cover, and we have this short exact sequence. And the point is that this group are not algebraic. I mean, you cannot embed them in a GLK. I mean, once n is equal or greater than 2. I mean, I'm not going to do any computations here, but if we do want to think about, I mean, have an explicit formula, which is, I mean, hard as the rank of the group increase, but for SL2, it's still doable, then you have this explicit formula for the multiplication inside the group. So what you see here that, as expected, you multiply two matrices on the left coordinate. The right coordinate is at mu n. You multiply them, and then you have this nasty cocycle coming. So this cocycle involves the Hilbert symbol, and it involves these X functions, which actually asks you which Haas cell are you lying in, the open cell or the closed cell. So there is some geometric flavor for this nasty creature. We should denote by S the map from SL2 to SL2 bar given by SG go to G, 1. This is a preferred section. This is not the homomorphism of groups, of course. And if A is a subset of SL2, then we denote by A tilde its pre-image in SL2 bar. A representation sigma of SL2 bar is called genuine if those central epsilon elements acts by epsilon. I mean, we don't want representation coming by inflation from the linear group or from lower degree covers. So we are sticking to these genuine representations. SL2 splits over UF via the canonical section, namely U is embedded inside the cover by taking this preferred section. And the inverse image of the torus normalizes this section. So we have, so the inverse image of the triangular, upper triangular matrices is again a semi-direct product of U identified with this section and the torus. And we study for the same reasons the principal series representations. Only now sigma is a genuine irreducible representation of the torus extended to the upper triangular. And I'm saying on purpose representation, not necessarily a character, because these pretty soon stop to cease being abelian. And precisely, I mean, it is easy to compute the cocycle on the torus. And it's just a Hilbert symbol. So it follows that H tilde is commutative precisely when n is equal to. Otherwise, these groups are not commutative. But they are not too bad either. They are just two-step nilpotent subgroups. And the isomorphism class of a genuine irreducible representation is determined by the central character. So we are maybe not inducing from a one-dimensional representation, but on the other hand, the inducing data is actually a character hidden there. Those are finite dimensional representations. Moreover, the central character may be then identified with a d power of character of f. D is either n or n, if n is odd, or n over 2 when n is even. So for example, when n equal 2, then d is 1, right? This is a manifestation of the fact that this is the only case where our torus is abelian. And this identification is canonical unless n equal 2 mod 4, in which case we must use the Veil index. From this point, chi will denote a character of f star, so that chi to the power d is associated, as explained above, by our inducing representation. Uniqueness of Whittaker functionals cease to hold once we move to covering groups. Okay, this is the theorem of Gao, Shahidi, and myself. Uniqueness of Whittaker functionals holds precisely when the inverse image of the torus is commutative. And this, of course, true to any of the covering group people are interested, any of the Berlinski-Deligne covering groups. I proved initially that uniqueness of Whittaker of functionals for double cover of symplectic groups is unique. And then I've noticed that I'm actually using the fact that the inverse image of the torus is abelian. And it's very easy to show that if your torus is not abelian, then uniqueness would fail. The other direction is more subtle, and we recently proved it. If the torus is abelian, then you have uniqueness. But this seems to be quite rare when you study covering groups. So, by what explained earlier, for n greater than 3, uniqueness of Whittaker model fails for SL2. The space of Whittaker functionals on a genuine principal series representation is fine, though. I mean, it's not too bad. Let me discuss first the case when n equals 2. Yes.
Just in general, for any reducible, can you go back just the one slide earlier?
This theorem, yeah,
it's always fine.
It holds for any
irreducible
Berlinski-Deligne cover of quasi-split reductive algebraic. Yes, I mean it's all. The point is that you have the machinery for proving uniqueness of Whittaker model for algebraic groups, and that this machine will work as well for cover groups, provided that your torus is that your metaplectic torus is abelian.
No. I was just saying you're right. The space of Whittaker functionals on a genuine principal series is finite, but I think on an arbitrary irreducible representation is finite. Finite.
On an arbit, no. I mean, probably the answer is probably yes, but I don't know where it's written. It's fine. I think. I mean, heuristically, the biggest space you will have for the principal series representations, right? So, I mean, it must be right. I'm not sure at this point where I mean, for a reference or if it's even written, but I'm sure it's finite anyway. Anyway, for principal series representation, this is just the dimension of the Whittaker function is just the dimension of the inducing representation, which is finite. Okay. So let me go back to the n equal 2 case. This is the only case where we actually have uniqueness of Whittaker model because the torus is abelian. And one has the Lang-Shahidi theory, namely you have local coefficients of SL2 bar. You have you have this Eisenstein series Fourier coefficients which are Eulerian. This was part of my PhD project. And in particular, you can define an analog of the local coefficient. And when you compute it, you hit up on this integral, which is precisely the integral representing the metaplectic gamma factor I introduced earlier. This is one of the main reasons why I introduced it. So Shahidi local coefficients for the linear group are Tate gamma factors, and for the double cover of N, this is the metaplectic gamma factor. Suppose that N is greater than 3. This is the project of, those are the last two papers, 2 or 3 papers of Gao, Shahidi, and myself. We have used Jacquet integrals to identify both spaces of Whittaker functionals with the space of functionals on the inducing representation. So now we have an actual matrix representing a map between 2 different spaces. You know that generally you don't have a map representing you don't have a matrix representing a map between 2 different spaces unless you somehow beforehand identify them. This is precisely what we did by using those Jacquet integrals introduced earlier. So we have this matrix whose characteristics polynomial is an invariant of the representation. Once you pick a natural basis, you hit on linear combination. You hit on linear combination of epsilon or epsilon bar, epsilon tilde factors as entries. This means that our work provided a new interpretation for the scattering matrix introduced by Kashdan and Patterson in the 80s. So a closely related object, which is not invariant, was computed ad hoc by Kashdan and Patterson in the 80s. They were after the rank, which is independent of choosing bases. And they use this matrix to compute the dimension of Whittaker space on the theta representations. And then this matrix, which was only available in the unramified cases, was computed by McNamara for, much larger class of groups. And those are nasty objects. It's hard to make sense of the entries. While in our construction, the entries are crystal clear. And we can, of course, recover Kashdan-Patterson matrix by our matrices. And then we have invariants. So first, the Planck-Charel measure. We can compose 2 matrices and compute the Planck-Charel measure. And this is what you hit on. You seem to have a unified theory, namely you have a nice formula depending on N. And then, of course, you want to use the Planck-Charel measure to answer the reducibility question. For this, you need to have a metaplectic Napstein dimension theorem. So Napstein dimension theorem was generalized by Savin to some parabolic induction covering groups. So there are 2 Savins here, but only one Savin actually did the work, including the case we're interested. And very recently, Kaiwa Lu, who is a postdoc in your department, extended this theorem to any parabolic induction on covering groups. So we can use the analytic properties of this explicit function and show that if n is even and sigma is unitary, then I sigma is irreducible. And if n is odd, then the reducibility results goes the same way as in the linear case, without explaining exactly what's the same way. But the point is that if you're looking at these 2, then you seem to have a dichotomy. The even fault covers goes together and the odd fault covers are a separate group. But surprisingly, this is not quite Suppose you would compute the trace. It's an invariant of your inducing representation. So the trace happens to be some average of gamma factors. This here, I mean, the O here is a redundant. This is just the inverse of the dimension of the inducing representation. And you see that unless n equal 2 mod 4, you're looking at gamma factors, and otherwise you're looking at gamma tilde, at average of gamma tilde factors. So now it seems that the odd fold covers and the 4-fold covers are one group, and the 2 mod 4-fold covers are grouped together. But then when you try to actually compute this average in the unramified setting, what you find out that you have one formula, although they're quite the same, depending only on the degree here. You have only one formula for the odd fold covers and the 2 mod 4-fold covers, and one for the 0 mod 4-fold cover. Determinant is probably the most important invariant here, since it's multiplicative, and local coefficients are expected to be multiplicative once you move to larger groups and you choose your Weil element carefully.
You mean compatible with?
Come again?
You mean compatible with parabolic induction?
I mean,
multiplicative. You mean compatible with parabolic induction?
Yeah, right. I mean, in the linear case, then you know that if you take two Weil elements with no cancellation, maybe that the length of the product is the sum of the lengths, then you know that the local coefficients are multiplicative. And whatever invariant you can define this way, you expect it to be multiplicative in this manner, which may be also called compatible with parabolic induction once you take induction by stages or something of this nature. By definition, right, since the product of the two determinant is the Plancherel measure to some power being the dimension of the representation, just because the product of these two local coefficient matrices is a scalar matrix. And you can compute it in the unramified case. And what you hit is complete trichotomy. You have gamma factors if n is odd, and Plancherel measure. You have metaplectic gamma factors and Plancherel measure if n equal 2 mod 4, and you have only Plancherel measure if n equals 0 mod 4. We've computed these determinants for other unramified inductions on other groups, and it turns out that you always have either gamma or gamma tilde or none. You never have both. And all these are what we call the SL2 trichotomy. I mean, it's not exactly clear to us why do these three types of cover, odd, 2 mod 4 and 0 mod 4, all behave differently. And it's not even explained by, to the best of my understanding, by theory of L groups of Weissman. But here is what we can cook from this determinant. We can cook a new invariant. If n is not 0 mod 4, which is the case where we actually had those gamma factors, then the dimension of the inducing representation is odd. So you can define a new invariant by dividing it by a certain by dividing the determinant by a certain power of Plancherel measure. Once you divided it correctly, the product of these two invariants is a Plancherel measure. And by the previous slides, this invariant is either a gamma factor, an actual gamma factor, or a metaplectic gamma factor. So what we've seen here is how to attach a gamma factor in a natural way to an induced representation on covering groups by starting with simpler objects, which mean determinant of the local coefficient matrix and the Plancherel measure. This gives us great hope that this local coefficient matrix has some arithmetic in it, has some automorphic representation theoretic significance. Finally, and this is the part of the story I'm not telling you, I'm already 4 minutes late, is what's happening when you go to GL2 bar. There is families of C-twisted n-fold cover of GL2. And even when you fix the N and you vary C, those are all those are typically generically non-isomorphic groups. Nevertheless, all of them has SL2 bar as a derived group. And it turned out that this trichotomy we encountered is gone once we move to GL2 bar. I mean, there is no distinction here between the degree of the cover. This is quite surprising because the local coefficient matrix and these invariants are determined on the level of unipotent elements, which all lies in the derived group. This gap is explained. I mean, this is part of our work by the nature of the restriction from GL2 bar, GL2 tilde to SL2 tilde. This restriction is very different from what some of us knows from the linear group. And we also need some subtle relations between the 4 arithmetic factors introduced earlier. So I think I'll stop here. I hope it wasn't too much. Thank you very much for your attention.
Let's thank the speaker. Questions, remarks, comments?
Yes, I would like to ask just that I think 3 slides back, you said that the theory of L groups does not, when you, yes, right, this one. Yeah. You said that the SL2 trichotomy is not explained, but at least I think that the L group for coverings of SL2 is one thing when n is odd and another when it is even. So at least
you're absolutely correct. You're absolutely correct. And if we would have stopped here, if we would have stopped here on the level of Plancharel measure, and this is actually where I stopped before I got deeper into this a couple of years ago, then I would say exactly this. This is compatible with the fact that you have 2 different L groups depending whether n is even or odd. So on that level, you're absolutely right. This is explained by the theory of L groups for covering groups. But this, I mean, why does the 0 mod 4 cover behave so differently than 2 mod?
No, of course that doesn't. Of course, that case is not obviously, yes, that's true.
Yeah, so I mean, a dichotomy is explained, but by L functions, but by L groups, but not this trichotomy. I mean, we don't see any good reason why it happens, only that it's there.
Or that the L groups machinery is missing in part. Something is missing there.
Yeah, I mean, at this point, it's a mystery. And it's even a greater mystery, why is it gone once you move to a cover of GL2? There is some fertile ground here.
But at least there is just one L group. At least there, for all Kasdan-Patterson coverings, it's the same, right? That one doesn't depend on C, or it does.
I mean, depend weakly. The C appears the rest. I mean, the covering group, no. The covering group.
No, the L group. The L group.
The L group.
Right?
Yeah, the L group is independent. And the picture is quite unified. You have some very weak dependent on the C. I mean, to me, an insignificant one. But what's going on in the SL2 bar level and the way it's dissolved when you move to GL2 tilde, I mean, for me, it's a great mystery at this point.
I have another question regarding the, this goes a bit earlier, you mentioned that F star n is of a finite quotient in F star, yeah. So I was wondering if at any point you actually used the structure of this group. I mean, at least for n equals 2, you don't have, I mean, it's always the Klein group. If the structure.
No, it's the Klein group.
No, I mean when F is p-adic. When F is
no, it's not the Klein. I mean, it's not the 4 elements Klein group.
That's what it's not.
When P is equal to, when you're.
No, except when P equals 2, right?
Yeah, and one thing that I can tell you that except for the unramified computations, I mean, our result works equally. I mean, we don't care about the tame assumption.
Right, but so you don't use the structure of the. I mean, you could, in theory, try to understand how the structure of this group implies some properties, but you don't.
Well, of course, when we do ramified computations or when we try to guess what's going on, we look at the time case, sure, and then we take advantage of it. But actually, I think it's more or less the other way around. I don't care about the structure, the actual structure of this group.
Okay. More questions, comments? If it's not the case, so let's thank the speaker again. And see you in a week. I'm not stopping the meeting, so everybody who wants to discuss informally is most welcome for about half an hour.
Thank you.